Okay, so in this video, we are going to discuss the generalization of the notion of vectors. And we already have done this by looking at R4, R5, and in general Rn for an arbitrary positive integer n. But let's just go over it and get a feeling for how we actually were able to generalize our notion of vectors, right? Geometrically, we think of a vector as a line segment in space that has length and direction. So we have R2 naturally, the set of vectors in the xy plane. And if you remember, there are two ways of expressing R2. You can write R2 as the set of real tuples, or you can think of R2 as the set of column matrices with length 2, with two components. So where x and y are arbitrary real numbers. Well, we can visualize line segments with direction, so directed line segments also in R3 in the three-dimensional Euclidean space. And all that is the set of triples of real numbers, or viewed as column matrices, the set of column matrices of length 3, so with 3 components. And in both cases, we can visualize what the vectors look like as explicit directed line segments, right? If I give you the xy plane, and I gave you two coordinates, an x and a y coordinate, you can actually visualize the vector. Same in R3. I can give you the coordinates of the three-dimensional space. And if I give you an x, a y, and a z component, you can also visualize a vector as a directed line segment. Say it points this way. And then the question is, well, it's hard for us geometrically to extend our concept of vectors because we are limited. We only see with our own two eyes things in 3 dimensions. And then you say, well, okay, how do we extend, if at all possible, our notion of vectors? Geometrically, it may be hard to imagine, but algebraically, it is very simple. We said, well, we can look at matrices that are column matrices of length 2, so 2 by 1 matrices. We can algebraically very simply add a third component. And again, algebraically, very simply look at R4. What if we add a fourth component to our vector? So consider the space of 4 by 1 matrices with real components. Where each xi is an arbitrary real number. So you see, algebraically, it was very easy to go from 2 components, 3 components, 4 components, or in general Rn with n components, right? For any positive integer, you can consider the set of all n by 1 column matrices. So x1, x2, up to the nth entry xn. And as before, xi, ranging from 1 to n, is an arbitrary real number. So we consider all n by 1 column matrices. And even though it's harder for us to imagine vectors with 4 components, we can still think of these column matrices, even though they have more than 3 components, as actual vectors in space. Directed line segments with now 4 components, or in general, n components. So we were able to extend our notion of vector through algebra. It was very simple to algebraically extend our vectors. And then the algebra allowed us to still treat these new elements as we did for vectors in the xy plane and vectors in the three-dimensional Euclidean space. And so you see that the algebra gave us a chance to try and extend the geometry. And if you remember, with the help of the dot product and the Cauchy-Schwarz inequality, we were able to show that the concept of length still makes sense, and the concept of angle, or angles, still makes sense. And so this was a first example of the algebra allowing us to extend our geometric notion of vectors. And the natural question is this the end of the generalization? Is this the full story? And the answer is actually no. We can generalize vectors, the notion of vectors, one step further. And the idea will be, as it was in R4, R5, and beyond, to extend our geometric notion of vectors algebraically by adding components, as in the case of R4 and beyond, and using the algebra, the dot product, and the Cauchy-Schwarz inequality to get concepts of norm and lengths in these slightly stranger spaces of vectors. The only question is now, what is the algebraic extension? What kind of algebraic properties, rules, will allow us to consider more general spaces of elements as also spaces of vectors? And we will call these vector spaces. The question is now, what kind of algebraic rules will we need to be able to think of certain elements as actual vectors? And the answer is there are 10 properties. This may look a bit technical, but as you'll see, it's actually not that bad. To algebraically capture the geometric notion of vectors, we need to consider 10 axioms, 10 rules. So let's see what we have here. V will be our set. So we let V be a non-empty set. So we have at least one element in V. And it's a set equipped with two operations. There is vector addition. And if you notice here, I have a plus but circled, and scalar multiplication, so being able to multiply our elements by real numbers. And you may ask, well, why do I circle the plus and the times? The answer is that we can even generalize further and consider non-standard additions and scalar multiplication. In this course, we will only consider the standard addition of elements and the standard scalar multiplication, but keep in mind that we could define stranger additions and stranger scalar multiplications. So we said that the triple, so the space of elements, with the addition of elements and scalar multiplication is a vector space. And again, all this is a space of vectors. So you think of it as, even though on the surface the elements may not look like vectors, like directed line segments, because they satisfy the following 10 conditions, the vectors, the elements of the space V, may not explicitly look like vectors, but if the space V satisfies all of these 10 conditions, you can think of the elements of V as actual vectors, geometrically, therefore as directed line segments, in the same way we did for R4, R5, and in general Rn. Even though we couldn't easily visualize these spaces, we could still think of their elements as actual vectors. Let's look at these 10 axioms and see they are, for the most part, very familiar. And again, in the following discussion, you can think of the plus as regular addition, times as regular scalar multiplication. But keep in mind, it is possible to have vector spaces with non-standard addition and scalar multiplication. Look at the first axiom. It says if you take two elements of your space, so two vectors in V, if you add them up, the resulting vector is still an element of your space. That's the first property. Closure under scalar multiplication says if you take any real number, lambda, and any vector of your space, if you then multiply your vector by the real number lambda, the result is still an element of your space. Addition commutes, so if you take two elements in your space, u and v, well, u plus v is the same as v plus u. Associativity, if you take three elements of your space, u, v, and w, if you do u plus the sum of v and w, this is the same as the sum of u and v, and then adding up w. Axiom number 5 is the existence of the so-called zero vector, or the zero element. So in your space V, there has to exist a zero element, so we denote it by 0 with a vector, the zero vector, called the zero vector, such that Well, it really behaves like the zero element. If you add to 0 the vector u, or you add to u the vector 0, you get back the vector u. And this is true for any vector in your space. So adding the 0 element to a vector does not change the vector. So your space must contain a 0 element. Then there is the existence of a negative element. So for any element of your space, call it u, there has to exist an element that we denote negative u. It's called the negative of u, so that if you add u to its negative element, or the negative element to u, the result is the 0 vector. Once again, very intuitive. And these are properties of scalar multiplication. If you have a real number times the sum of vectors, the sum of elements of your space, u and v are elements of your space, you can distribute the scalar multiplication. You can do lambda u plus lambda v. Once again, a very familiar property. Property 8 says that for any two real numbers, lambda 1 and lambda 2, and any element of your space u, if you have lambda 1 plus lambda 2 times u, you can also distribute as lambda 1 times u plus lambda 2 times u. Once again, a very familiar property. We can distribute also a scalar multiplication onto a scalar multiplication. So if you do lambda 1, lambda 2 are real numbers, u is any element of your space. If you do lambda 1 times lambda 2 times u, you can regroup the two real numbers as simply lambda 1, lambda 2 times u. And finally, for any element of your space, if you multiply your element by 1, the result is the same. And if you look at these 10 axioms, they are very familiar. We've seen these many times before. And surprisingly, if you have a set of elements, whatever the elements are, and you will see that very shortly we will consider spaces of actual vectors, matrices, even functions. We will even think of functions as vectors. But as soon as you have a set of elements where you can add the elements together, and you can multiply the elements by real numbers, if the set with these two operations satisfy these 10 axioms, these 10 properties, this says to you that even though on the surface the elements may not look like vectors, you can think of them as actual vectors. So the geometry, all of the intuition that we have developed thus far about vectors will also carry over for vector spaces. The only question is, if we want to prove something as a vector space, will we have to every time prove that the set with the vector addition and scalar multiplication satisfies these 10 axioms? And the answer is no. But we will need to begin with a set of large vector spaces. So what are sets that we know of that satisfy all of these 10 axioms with the regular addition of elements and the regular scalar multiplication? So we will look at this as a remark. This is really an exercise. I will ask you to show that the following are vector spaces by going over the 10 axioms and making sure that in each case the 10 axioms hold true. So the following sets, and again here implicitly it is the standard addition of elements and the standard scalar multiplication, so the one we're used to. So the following sets with standard operations are vector spaces. So if you look, all of these 10 properties you know are all true for Rn for any n. So Rn, not surprisingly, is a vector space. So the set of column matrices of length n with n components is a vector space. And this is true for any positive integer n. Let's look at these 10 properties again. if you think of the set of all rectangular M by N matrices, all of these 10 axioms are also obviously true. And so the space, if you fix M and N, of all M by N matrices also is a vector space. So for any fixed M and N. So if you consider it a space of all 7 by 10 matrices, this actually is a vector space. So even though on the surface the elements don't look like vectors, you can still think of them as actual vectors. What else? Well, if you consider the space of all functions on the real line, these 10 axioms are also all true. So you can think of the space of all functions as a vector space, as a space of vectors. So the set of all real functions. So if you think of it, so functions from the reals to the reals. If you take all of those, you can check that the 10 axioms are true, and so we can think of the space, the set of all functions from the real numbers to the real numbers, as a space of vectors. They form a vector space. What else? Well, you can ask, what if we consider vectors with an infinite number of components? Is it still a vector space? This will be the space of real sequences. So R infinity again, think of them as a vector with the space of vectors with an infinite number of components, therefore as sequences. So x1, the first entry of our sequence, x2, x3. We have a sequence, an infinite list of real numbers, where each term is some real number. So the space of all real sequences, so infinite lists of real numbers, x1, x2, x3, and so forth, is also a vector space, right? You can think of basic addition of sequences and scalar multiplication, and all of these 10 axioms hold true, and they're all very easy to check. And I'll give you one last example. This is one you may have not seen before, but the set of complex numbers. Complex numbers are numbers of the form a plus bi, where a and b are arbitrary real numbers, and I is the square root of -1. This also is a vector space. If you think of it, think of I being some number whose square equals -1. Clearly I is not the real number, because if you square a real number, it will always be non-negative, and since I squared is a negative number, I is actually not a real number. But the space of all complex numbers is also a vector space, and it's not very hard to verify that all of these 10 axioms are satisfied. And this is now, as I said, an exercise. Make sure that in each case, Rn for any n, the space of all m by n matrices when m and n are fixed, the set of all real functions, the set of all real sequences, and the space of complex numbers, make sure that in each case you verify that the 10 axioms hold true. Therefore, all of these are vector spaces. So even though on the surface the elements may not look like vectors, we can think of them as behaving like vectors. Okay, and now the question is, once we have agreed that these are actually vector spaces, spaces of vectors, can we, for a lot of other sets, actually avoid having to check these 10 axioms? Knowing that these 5 spaces are vector spaces, can we take advantage of this fact so that when we encounter new spaces, we cannot, or we can avoid, I should say, having to check these 10 axioms and only a small number of them? And the answer is yes. And this is called the subspace theorem, and this will be the topic of our next video. how can we, knowing that these are vector spaces, how can we take advantage of this fact so that when we encounter new sets and that we want to check whether or not they are vector spaces, taking advantage of the fact that we know that these are vector spaces, do we have to check all of these 10 axioms every time? And the answer is no. But this will be the topic of our next video, and this will be called the subspace theorem.